Okay, so today we're going to be looking at the inclined plane experiment. Okay, so what we have up here is, so we have a right triangle and we have a cart that's going to roll down the inclined plane, as shown here. So we have a motion detector, a cart, and an incline. And we have it propped up on one brick. So what we're going to do is measure the acceleration as the cart rolls down the incline using the motion detector. And we're going to do 3 trials at 6 different heights. So we're going to have a bunch of experimental data for 6 different heights. Now we can also look at a theoretical acceleration, which is not written in the lab description. So we have the acceleration of gravity is always pointing downwards. But the cart's going down the incline, so we know it's going to be some component of the acceleration of gravity. So we know it's going to be less than the acceleration of gravity, quite a bit less. How much less? Well, that's what we're going to measure. And that's what we can also compare to a theoretical value. So if we have the angle theta, we can find the sine of theta as the opposite over the hypotenuse. So height and x we can measure, and then we know the sine of the theta. So we divide h divided by x, and that gives us sine of theta directly. Okay, so there's no need to use this sine or inverse sine functions on our calculator today. That value is directly the sine of theta. So now we look at this value. We can use similar triangles to show that this angle theta is the same angle theta here. So the sine of theta is opposite over hypotenuse, where g represents the acceleration of gravity of free fall, 9.81 meters per second squared, and gx represents a theoretical acceleration along the incline in that same direction. Okay, so this is going to be a theoretical. So we can write that as sine of theta equals gx over g. And before, from the height measurement, sine of theta equals h over x. Okay, we just solved that for gx, and this is going to be our theoretical acceleration on the incline. So it's our 9.81 meters per second squared times the sine of theta, which we found by dividing h over x. Okay, so you're going to want to add a column for this to your data table. Alright, again, it's not written in the lab description, but we're going to do that. Okay, so let's go to collecting the data. So to collect the data, we're going to open Logger Pro. And we have our program here. And it's connected to a motion detector, so we have a position time graph, velocity time graph. Now we want acceleration, so we know acceleration is the slope of a velocity time graph. It's the rate of change of velocity over time. Okay, so let's go ahead and collect some data and see what happens. So I'm going to hit collect here, and I'm going to release the cart. Okay, and we have some data here. Our position graph is steadily increasing. That means it's speeding up. Same, and our velocity graph has a linear slope, but an increasing slope. Again, that means it's speeding up, it's accelerating. So we can calculate, we can find the slope of this velocity time graph, and it gives us our acceleration. In this case, it's going to be 0.2675 meters per second squared. Okay, so 0.2. That's considerably less than our 9.8 meters per second, 9.81 meters per second squared. Okay, so that's how we collect the data. And we're going to do multiple trials at multiple heights. And you'll see that on the data it's provided. Okay, so once we collect all of our data, and you're going to find your average value, your average for your 3 trials, standard deviation of the mean. And we'll use the standard deviation of the mean to compare our average values to our theoretical values in a moment. Okay, so we're going to first plot, following the analysis section, we're going to plot a graph. Okay, so we're going to plot our average acceleration values on the y-axis and our sign values on the x-axis. Okay, so this is what our graph is going to look like. Okay, our average acceleration values on the y, sign values on the x. So we're going to use Excel. We're going to get some equation of a line, y-intercept, and a slope. So we'll have, how do we look at this? Really, our y-axis is acceleration, and our x-axis is sine of theta. So this is another way to rewrite this. And once you plot it on Excel, again, you'll have numbers for your slope and your y-intercept. So it asks you to solve this at 90 degrees. So how do we do that? Well, you're going to use the values of your slope and y-intercept, and you'll just input 90 for theta, solve the sine of 90 times your slope times your y-intercept will give you that value of acceleration that the question is asking for, and it asks you what does it represent. Okay? Okay, so now back to comparing our theoretical acceleration to our experimental. So here's some additional problems which I'm also putting on Blackboard. So again, you want to quote your values like this every time where you have standard deviation in your results section. This is how your values are quoted. Your average, and this is experimental, plus or minus the standard deviation of the mean. So you'll write those numbers out. So you'll have 6 of these. So for example, I'm just going to make up numbers here. 0.253 plus or minus 0.015 meters per second squared. So that's how you would, that's just a made up number, but that's how you would quote your results, okay? So in this case, you'll just have 6 of those. So how do we use that to compare values? So we want to compare our experimental, average experimental, to our theoretical. And that's what we had here again, okay? So we look at standard deviation as error bars. The reason we say plus or minus, and here's a representation, if this is our standard deviation, well, this gives us some range of predicted data. So plus or minus our average value. Now the question is, does our theoretical value, what do we call it, g sub x, does it fall within that range or not? If it falls within one standard deviation, we say they agree. If it falls within 2, which is somewhere up here, we say it's questionable. And if it's way somewhere out there, we say it does not agree. That doesn't mean it's wrong, it just means that the data points don't agree to each other, okay? And that's how we're going to analyze this. So it asks, Do they agree with each other? Well, we have to say, does it fall within 1, 2, or more than 2 standard deviations of the mean? So you'll do that for each of your six heights and your 6 average values, and you'll say each one agrees, disagrees, agrees, questionable, or does not agree. Okay, and the last part is, what if there's a difference between our theoretical and experimental, what could account for the difference? Is it a statistical anomaly, or is it some type of systematic error, something physical in the experiment that we can account for? Okay, so that's going to be the inclined plane experiment, and that should do it. All right, thank you.